Hey everybody, today we're going to solve the leaf similar tree problem on LeetCode. Here's the problem definition. We consider all the leaves of a binary tree from left to right order, which is important. The values of those leaves form a leaf value sequence. So we look at this tree, where are the leaves? Obviously 6, 7, 4, 9, and 8 are the leaves, being that they have no children. And the leaf sequence is 6, 7, 4, 9, 8. Just the leaves from left to right. And here's the leaf sequence: 6, 7, 4, 9, 8. Two binary trees are leaf similar if their leaf value sequence is the same. And we want to return true if the two trees we are given are leaf similar. So an important note here is each tree is going to have 1 to 100 nodes, meaning we don't have to worry about the root of either tree being null. So there's a little bit of code to write to get this done, but let's talk about how we're going to do it, and then we'll just run through and implement it really quick. So there's a bunch of different ways of traversing trees. You got pre-order, in-order, post-order traversal, depth-first search, breadth-first search, level order traversal. And for me, when I saw this problem, what made the most sense is depth-first search. Okay, so in a depth-first search, we will traverse down each branch as far as we can go, hitting if we set up our depth-first search correctly, hitting the left leaf first, and then it'll basically traverse down each branch as far as it can go before backtracking back up to the root and then traversing back down. So that's what our depth-first search will do. It'll traverse to each node, and the way we'll write it, it'll go to the left nodes first. It'll traverse as far down a branch as it can go, back up, and then traverse back down, back up, and then back down, and then back up again, down this branch, down to the left side, and then back up, and then finally here. So the depth-first search will give us the leaves in a left to right order, and we'll just do that for both trees and make sure that they match up. Alright, so there's a little bit of code to write for this. If you know how depth-first search works, it's usually based around the idea of a stack. So we're going to set up a stack for each tree. If I could type tonight, that would be great. Okay, so we've got our stacks, which will hold the nodes as we traverse through each tree using depth-first search. Now, I'm going to use a linked list to represent basically a queue. In Java, there's no queue data structure, so we just use linked lists when we find something that needs a queue. I'm going to push the start nodes onto the stack here. These shouldn't be stacks of integers, they should be stacks of tree nodes. Alright, so we're going to push the root onto each of our stacks here. Okay, so each stack now has just one node being the root, and now we're going to loop through and do our depth-first search. So while stack 1 is not empty, what are we going to do? Well, we're going to pop off the current node. Okay, so we pop off the node on the top of the stack, and we're going to figure out if this is a leaf by checking if both of its children are null. Okay, so what happens if, as we're traversing through the first tree, if we hit a leaf, we're going to add it to the leaves queue or linked list that we have set up. This is going to track the leaf values from left to right for us. Let's say it's not a leaf, then we need to push its non-nil children to be traversed down later. Similarly, for the right. Alright, okay. So that's going to be our traversal through the first tree. Nothing too difficult. Now we just got to traverse through the second tree. I'm gonna do something really bad in computer science here, and I'm gonna copy and paste some code. Yes, the more design savvy way of doing this is you would set up a method or something and pass it the stack that you want to traverse and all that, but it's LeetCode. Code. We can't be bothered with such things. Alright. So in this case we're gonna pop off stack 2. We're gonna check and see if it is a leaf. Now in this case we're gonna treat the leaves a little differently. Instead of adding the leaves, we're just gonna do if the first value, which is peak. Peak lets us look at the first value in our queue without actually taking it off. I'm going to say what happens if it is equal to the current value. Well, in that case, we're going to take it out using poll, which will remove the head of the queue. And the case where it's not a... I put stack 2 up here. This should be 1. I was wondering why it was already taken care of for us. Alright. And then down here at the bottom, we'll just return leaves is empty. So what does that mean? That means if we get to the bottom of the traversal of both, because of the way that we're evaluating the leaves here, and taking off the leaf if it's equal, then now the leaves have to be empty. And they'll only be empty if they're equal. So let's see if we're going to get any syntax errors there. Looks okay. Let's find out if there are any logic errors. Alright, accepted solution. Cool. So, tree problems, you just need to know your different modes of traversing trees. If you're gathering up leaves, that first search makes a lot of sense, because we traverse all the way down a branch, and then we traverse down the next branch, and then so on until we're done. You know, sometimes a level order traversal, if you're looking at things on the same level, but level order traversal would have been problematic here because, you know, these leaves are on a level, these aren't, and it would have been a problem, and that would have gotten messy. So just picking the right traversal algorithm makes a big difference. Yeah, so that's it for this one.